So welcome to my talk. I'll just start with explaining what text zoning in the context or for job ad is, and also explain what it's good for. But then we'll have a quick look at our data and the machine learning methods we applied. I will show you then most important results of our experiments, and if there's time, also a short error analysis, and come to a short conclusion. Okay, text zoning in for job advertisements means just segmenting job ads into different text parts, and these text parts differ from each other regarding their content. So it aims at capturing text parts that are dedicated to particular subjects or topics, like for instance the publishing company. And in our corpus, the Swiss Job Market Monitor corpus, we have 38,000 job ads in German from 1950 to 2014 that are manually segmented into these eight different text zones that I will show in the following. The most important text zones for our own labor market research are Zone 1, the company description. This covers, for instance, a phrase like ein erfolgreiches Unternehmen der Baubranche. Then Zone 6, the job description. It covers everything about the task, working condition like working hours, and so on. Then Zone 7, the required hard skills like experiences, education, and so on. And required soft skills, Zone 8. A sentence like Sie sind belastbar, zuverlässig und diskret would be a part of this text zone. And furthermore, we distinguish the reason of the vacancy, administration and residual text is everything about the application procedure, for instance. Job agency description, this applies only if a job ad is not published by the company itself, but instead by some placement service, and incentives like salary and fringe benefits. So let's have a look at a zoned or segmented job ad. We segment on a token level. So here we can see each token with its corresponding zone tag. And the colors here are just for you to identify the new zones. So a zone can consist of a single token, but usually it contains longer parts like phrases, sentences, or sometimes whole paragraphs. And of course, not every job ad has information on all the zones, so most often there's nothing or no information about the reason of the vacancy. And on the other hand, a single text zone can show up several times. Like here we have information about the job in the beginning, like just the job title, eine Dekorateurin, and then later on here we have more information about the job task. So what is this good for? First of all, we can localize text parts of interest more precisely, and it allows also disambiguation. Firstly, disambiguation of words with one meaning, and most importantly, it helps us to decide if a text part actually refers to the subject we're interested in. So imagine, for instance, that we would like to extract the required soft skills for a position. For instance, the soft skill dynamic, then it's extremely helpful to know if the keyword dynamic actually refers to a dynamic personality, like in the first example, or if instead this refers to a dynamic working atmosphere or to a dynamic CRM system, which would just be the working tool. So in this way, text zoning facilitates information extraction, or in more general, we can say that it provides structure to the job ad and represents an information gain that can potentially be useful for a broad range of NLP methods that we apply in social sciences. What is our data and machine learning strategy? As I mentioned, in our corpus we have 38,000 job ads, only German job ads that are segmented in these zones. Job ads are from the press, company websites, and online portals, and from the time period 1915 to 2014. So we have quite a large amount of data that we can use for supervised machine learning. And we use 80% of this data as train set, 10 as development set, and 10 as test set. We train our models in 50 iterations and always keep the model that performs best on the development set for further evaluation. So, and we evaluate just global accuracy, precision, and recall, always on a token level. And The task is, as you have seen, a one-label multi-class classification on the level of token sequences, and we tackle this with recurrent neural networks. But before I say a bit more on that, I just want to give you an impression of the difficulty of the task. One difficulty is that we have quite a skewed class distribution. So the two largest classes have 30% of the tokens each. This is just the job description and the administration. And on the other hand, we have three minority classes with less than 5% of the tokens each. And secondly, we have a high class ambiguity of the tokens. So 50% of the tokens have been seen in all 8 classes. The largest part of these tokens is just function words, which usually just adopt the text zone from their neighbor tokens. But also, the largest part of the other tokens have been seen in more than one class. So this implies that our classification cannot rely on token information only. Instead, we need to consider, or we need context for the classification. And so that you get an idea of the baseline, if we just would use the majority class as a baseline, we would reach accuracy of 30.5%. And in earlier approaches with conditional random fields, we achieved accuracy of 87.8%. For the methods, we use bidirectional long short-term memory networks. One advantage is that they consider context on both sides for the classification of the actual token. And another advantage is that they integrate well information over long sequences, so they're good in remembering which information to store and which to forget. And this makes them ideal for a sequence labeling task like ours. Feature engineering here was rather simple. We just had word embeddings as only input to the networks. And in our experiments, we tested pre-trained embeddings, the concept net number batch embeddings, as well as task-specific embeddings. And kind of a special feature is that we use character level representation for our words. Since there's much more data on the character level, this should help us to find a better generalization. And we implemented this with the DINET toolkit. We used the neural network architecture developed by Huang and colleagues as starting point. So basically, we have just bidirectional LSTMs on the token level to encode the input, and then we have a multi-layered perceptron on top. So we just concatenate output vectors from forward and backward LSTMs and give them as input to the MLP. And for the rare words, we have, again, forward and backward LSTMs on character level, concatenate output vectors, and fed them as input to the token level LSTMs. And in our experiments, we also tried to change the hyperparameter setting, but the only change that had a noticeable effect on performance was to add a second layer to the token level LSTMs. So our final model is basically the same as Wang and colleagues developed, just with a second layer on the token level LSTMs. Okay, so let's start with the results. Firstly, we wanted to test if pre-trained embeddings work better than task-specific embeddings. And in our original model with task-specific embeddings, we reached accuracy of 89% on the token level. And you can see here that the use of pre-trained embeddings does not improve model performance. If you use the concept net embeddings without fine-tuning, then accuracy is clearly lower with 86.5%. And we've allowed them to be fine-tuned during the training. Performance improves quite strongly, but still it's slightly lower than in our initial model. So this implies that the task-specific training, or at least adaptation of the embeddings, is useful for our task. And secondly, it suggests that we have enough training data to learn a good task-specific representation. So as we have seen, the large amount of training data that we have in general is very useful for us. Another question is, how useful is older training data? Because one objective was also to build a model that is optimized for present-day JOVATs or even for future JOVATs. And in order to find that model, we built a test set with ads from 2010 and 2014, and then built models with training data from different time periods. And as you can see from the table, to go back in time and add more older data raises or improves performance, but only up until 1970, and then performance is lower again. So it seems that the effect of more data is partly weakened by kind of an out-of-domain effect of older data. And conclusion of this experiment was that the model with data from 1917 onwards seems to find the optimal trade-off between a training set that is large enough and up-to-date. And then as a final step to improve our models, we used the ensembling technique. That is, we trained 5 models with the same setting but with different random initial parameters. And then we aggregated classification. That is, we just used the majority vote of the 5 models as final classification. And one benefit of this technique was that we raised accuracy by 0.5%, which is the largest improvement of all experiments. And the second and even more important benefit for us is that it allows us to identify the text parts where the model don't agree, so we can correct them manually. And by doing so, we would reach accuracy over 90%. And so far, I've only been talking about global accuracy. Here you can see now evaluation for the single zones. So for the most important zones, the company description, job description, hard and soft skills, both precision and recall vary around 90%, except from the required soft skills, where recall is somewhat lower. And for classes that are not so frequent, like reason of the vacancy, incentives, and job agency description, the values, especially recall, is much lower. So obviously, where data is more sparse, classification is more difficult, which comes to no surprise. But still, the results also for these minority classes are reasonable in a way. And now we can have a closer look at error analysis. So here we see the confusion matrix. Vertically, you can see the model prediction, and horizontally, the truth according to our manual annotation. So all the green values are correct decisions, which sum up to almost 90%, and all the other cells are errors. So for instance, for 1.2% of the tokens, the model said this is part of the job description, where according to our manual annotation, this is part of the company description. And we can see that this is one of the most frequent problems. Here we have the highest value, like the distinction between the job description and the company description. And a second quite frequent problem is the distinction between the job task and the required soft skills. Here we have also values above 0.5%. And the third main source of confusion is confusion with Zone 3, the administration and residual text. So what are the reasons for these errors? The first confusion between company and job description can best be illustrated by the word team. Team can refer to the company as a whole, as well as to a very small working group, and correspondingly, team is among the most often wrongly classified tokens. And similarly, we can say that for information about the department or the infrastructure or the working environment, it's sometimes difficult to decide if this refers more to the company as a whole or to a specific open position. And the second confusion between the job description and the requirements appears because they can be wrapped up in one and the same text part. For instance, in a sentence like, Sie gehen offen auf unsere Lernenden zu und unterstützen diese mit ihrem Fachwissen jederzeit kompetent. Here also for human annotators, it's quite difficult where to split the sentence into the task and into the skills that are required to perform the task. And the third source of errors with the administration and residual text, this is related to the fact that the text is not always split up at the same level of granularity in the gold standard. So here in our beginning, in the example, in the beginning, wir suchen is here in the gold standard part of the residual text, but this was not always done exactly this way. Often it's also like just part of the following zone, which here are the soft skills. So here we have an error because the model already classified this as part of the soft skills, but since we are not so much interested in text parts like wir suchen, they're rather meaningless for us, we consider this rather to be a soft error. And to get back to our example in the beginning, as we can see here, eine dynamische Persönlichkeit was correctly classified as part of the soft skills. So if we are interested in extracting the soft skills, our automatic test zoning solution here is useful. So to get to a short conclusion, our experiments show that the optimal model setting for us is to use task-specific embeddings instead of pre-trained ones, to use token-level LSTMs with an additional hidden layer. If we want a model that is optimized for nowadays or current job ads or even future job ads, we should only include training data from 1917 onwards. And the ensembling technique has been very useful for us in improving performance and in better control of classification results. And with this setting, we reach an accuracy of 89.8% on the final test set. And compared to previous approaches with conditional random fields, this is an error rate reduction by 16%. For the text zones that are most important to us, we have recall and precision around 19%. So we can conclude that we built a solution for text zoning for job ads which is quite well performing and which should facilitate us the subsequent information extraction. Cool. Thank you.
So, a very specific topic, text zoning in job ads, but with general methodologies. What are your questions?
Yeah, thank you. So my question is, why you model this as a token prediction problem and not as a sequence labeling task? Because if I understand correctly, you concatenate the LSTMs and then you do an MLP and predict the token label.
Yes.
But you lose the global information of the structure of the document and the sequence of the labels. So you don't know at a token what you've predicted before. So my suggestion or question would be, why not use a CRF on top of that, for example, or use like an encoder-decoder model which captures these dependencies in the sequences?
Well, actually, we tried a global decoding model afterwards, like with a Viterbi algorithm, but it did not improve performance. So it seems that bidirectional LSTMs already by themselves are quite good enough in considering the context.
Yeah, but not from the labels, just from the text.
Yeah, right, but still, maybe there are other models of global decoding that we could try, but the one we tried had no effect at all.
Did you say anything about the languages in your job ads?
Yes.
Is this all for German?
This is only for German. We have, in general, well, mainly 3 languages in our corpus, but this kind of annotation, we have it only for the German job ads.
Any speculations how well it will work for French or English or other job ads? Is that pretty much the same task, or do you expect other issues there?
I would expect it to be quite a similar task, as I think French and English job ads show pretty much the same structure, but we have to try it out.
My question is that you type in, I don't know, data scientist in jobs.ch, right? And then all sorts of stuff that
I see your point. Yeah, of course. I mean, it's some kind of a pre-structuring to information extraction. In this way, it could be helpful for any kinds of deeper analysis. I don't know if you just type data analysis, you just have maybe too many options. So, but yeah, in general, I mean, that's the main reason why we do it, because we want to extract information more precisely.
Right, but you're not filtering for any job applicants, but you do research
we do
on the kind of changing requirements that companies are doing.
That's exactly true, yeah.
Job adverts, especially for large companies, the systems that create these adverts often have blocks of standardized copy.
Yeah.
Will the fact that the large employers are using these standardized copies distort the overall results, especially when you consider small organizations who may be handwriting?
The only effect that we could see is that if we do our analysis separately for the different advertisement channels, like print, company websites, and online job portals, then we can see that the results are for the company websites are a bit better, and that is because there we have a larger amount of ads from the same source, so with the same text parts. But other than that, it was quite impressive how robust this is also for very untypical job ads.
A question about this text genre, perhaps, and goes very well with what you said. Has the fact that job ads these days are more in the internet, has this changed the text genre considerably, or do they look differently than 10 years, 15 years before?
Maybe I can show a little graphic on that, if I'm here. They just got much longer over time. Oh, it's not here. Okay. So, the main change is that job ads got much longer over the time, and text parts that show the most important growth are the description of the company itself and also of the job task. But other than that, it's really fascinating how the general structure of what is mentioned in a job ad stays the same over the time. It's just the vocabulary inside the zones that changes because of job titles and tasks and required skills, and of course that change over time.
One of the findings from Sophie was that typewriting is no longer a skill that doesn't appear in job ads.
True.
Okay, if there are no more questions, then I'm closing the session. Thank you very much, and thanks to Sophie.